We are going to discover incredible things that we never imagined.
According to renowned astrophysicist Neil deGrasse Tyson, the James Webb Space Telescope may have found alarming proof of another universe in addition to its breathtaking views of the cosmos. Imagine living in a world where our comprehension is stretched to the limit and where we may not be alone in the cosmos. Our understanding of time, space, and existence itself may all be completely altered by this intriguing revelation. What is this other universe all about, then? Is it the only one like it? What are the opinions of professionals regarding this phenomenon as a whole? Let's inquire. Are we the only universe? What is existence all about? Is it possible for you to have multiple forms? And what if the universe is more expansive than the reality you currently inhabit? The questions are not new. The notion has been tossed around by philosophers, scientists, and storytellers for millennia. We now get at the multiverse theory, which postulates that our world may be one of many. This theory's foundations are found in cosmology and quantum mechanics. Physicists such as Hugh, Everett III, and Erwin Schrödinger established the foundation in the early 20th century with hypotheses that went against what we typically thought was true. Every quantum event might give rise to parallel universes, each of which would reflect a distinct result, according to Everett's 1957 many-worlds interpretation of quantum physics. This represented a significant shift away from the notion of a single, predetermined cosmos. And it makes a huge difference. Really, everything. It suggests that there might be an infinite number of parallel universes. You may be a trillionaire in one world while struggling financially in another. Another way to explore the multiverse was made possible by developments in cosmology. According to scientist Alan Guss's inflationary theory, which was put forth in the 1980s, fast inflation during the early stages of the Big Bang would have led to the isolation of certain regions of the universe, creating separate pocket universes inside a larger multiverse. These worlds may differ in their dimensions, physical rules, and constants. Over the past few decades, the multiverse theory has progressed from a theoretical notion to a subject of significant scientific inquiry. According to string theory, one of the most ambitious theoretical physics frameworks, our universe might be one of several that exist within a wider string landscape. Different string configurations, which are the basic building elements of existence, could produce these universes. Furthermore, it is thought that the cosmic microwave background radiation, the Big Bang's afterglow, may provide proof of extraterrestrial contact. The existence of the multiverse may also be revealed by high-energy cosmic rays or gravitational waves, according to theoretical scientists. As we move away from the boundaries of science, we may also observe that the multiverse idea has been completely adopted by fiction as a potent narrative device, with its philosophical and emotional ramifications explored. The classic example is 2001: A Space Odyssey, directed by Stanley Kubrick. The film's mysterious monoliths, especially the one seen close to Jupiter, appear to serve as portals to other worlds or higher realms. In the film's final scene, astronaut Dave Bowman is taken to a strange, unearthly environment that defies logic, implying that he has encountered a more expansive multiversal reality. In a similar vein, Interstellar, directed by Christopher Nolan, provides yet another powerful illustration of multiverse-like ideas. At the end of the movie's investigation into time, gravity, and higher dimensions, Cooper, the main character, enters a tesseract, a four-dimensional structure made by highly developed entities. Because of this tesseract, Cooper is able to interact with the past and future at the same time and view time as a physical dimension. The film gently raises the concept that there are other worlds or realms that are not visible to us yet are all deeply entwined with life. The multiverse theory is currently leading the way in cosmological studies. Additionally, the James Webb Space Telescope can aid in our understanding. How the James Webb Space Telescope aids in our cosmological research. The James Webb Space Telescope, or JWST, is a significant advancement in humankind's capacity to investigate and comprehend the universe. In order to completely understand its importance, we must start with the Hubble Space Telescope, which was introduced in 1990. With its position outside of Earth's atmosphere, Hubble was able to provide previously unheard of clarity by taking close-up pictures of far-off galaxies, nebulae, and areas where stars are forming. Over the course of 3 decades, it helped make important findings about the atmospheres of exoplanets and the accelerated expansion of the universe, which gave rise to the idea of dark energy. But Hubble was limited in what it could do. It was mostly visible and ultraviolet in wavelength, and it had trouble getting through the thick gas and dust clouds that form planets and stars. Furthermore, even though its 2.4-meter mirror was groundbreaking at the time, it limited its capacity to see far-off and faint objects. The necessity for a more sophisticated observatory was obvious. The idea for JWST, a replacement for Hubble, first surfaced in the 1990s. The telescope is named in honor of James E. Webb, a NASA administrator who was instrumental in the Apollo program and represents the spirit of exploration and tenacity. JWST was designed to function in the infrared spectrum, which is essential for studying the early cosmos since cosmic expansion has stretched light from the first stars and galaxies into infrared wavelengths. Innovative engineering was needed to achieve this focus on infrared, from its enormous 6.5-meter segmented mirror coated in gold to maximize reflectivity to its 5-layer, tennis court-sized sunshield that blocks heat from the sun and earth to enable the telescope to operate at extremely low temperatures. Additionally, JWST is based in the second Lagrange point, or L2, which is 1.5 million kilometers from Earth, in contrast to Hubble, which orbits the planet at the more manageable height of 547 kilometers. Although it offers a steady environment for observations, astronauts are unable to service it from this position. Every part of JWST was painstakingly made to be accurate and dependable. Made up of 18 hexagonal beryllium mirrors, its segmented mirror was intended to align and unfurl in space. In order to keep its sensors at cryogenic temperatures, the sunshield had to withstand the harsh conditions of launch and deploy without a hitch, which required more than 300 single points of failure. Because of these difficulties, JWST's successful December 2021 deployment was a historic accomplishment. One must consider that public enthusiasm in space exploration declined following the Apollo missions of the 1960s and 1970s as attention turned to other terrestrial priorities. In order to fully understand the historicity of this deployment, the launch and initial achievements of JWST have renewed a global curiosity with the cosmos, but the Hubble telescope, with its breathtaking photos, rekindled part of that passion. It has captivated people all across the world with its capacity to look into the early history of the universe, revealing the formation of the first galaxies and examining exoplanets in previously unheard of detail. The success of the telescope is a testament to humanity's ability to work together on large-scale projects, as NASA, the European Space Agency, and the Canadian Space Agency all contributed to its construction. Transformative insights have already been provided by JWST since its launch. Amazing discoveries from the JWST, a new era of exploration has begun thanks to the James Webb Space Telescope. In October 2023, for example, it revealed a fast-moving jet stream on Jupiter. This occurrence was unprecedented, even though it was more than 3,000 miles, 800 kilometers, broad and traveling at an incredible 320 miles per hour, 515 kilometers per hour, through Jupiter's atmosphere. Its ability to support life was further supported by the JWST's discovery of carbon dioxide in the deep waters of Jupiter's moon Europa. The JWST has demonstrated its potential to reimagine familiar celestial neighbors through the lens of infrared wavelengths by capturing breathtaking new images of Saturn's ring system and Uranus's delicate rings and brightest moons. Methane and carbon dioxide were recently detected in the atmosphere of the 120 light-year distance exoplanet K2-18b. K2-18b may therefore be a Hycean world, with seas of liquid water below and dense, hydrogen-rich atmospheres above. These planets might have the ideal environment for life. Nearer to home, the JWST unintentionally discovered a tiny asteroid trapped in the asteroid belt between Mars and Jupiter, about the height of the Washington Monument. Meanwhile, galaxies with massive masses and mature red stars that were only 500 to 700 million years after the Big Bang were discovered by the JWST. These galaxies appear excessively massive and well-developed for their epoch, which suggests that cosmic history may have evolved differently than previously believed. These observations also challenge popular hypotheses of early galaxy formation. The ongoing controversy over the pace of expansion of the cosmos has also been heightened by the JWST. Differences in the value of the Hubble constant have been brought to light by the observation of Cepheid variables, enormous stars that are crucial for determining cosmic distances. It has also transformed our knowledge of the early universe, discovering structures and occurrences that go against accepted cosmological beliefs. For example, scientists have discovered intricate chemical compounds in a galaxy that is more than 12 billion light-years away. These molecules, which resemble those in coal and oil on Earth, are connected to dust grains and release infrared light. The foreground galaxy's ability to magnify the background galaxy where these molecules were found by acting as a gravitational lens is what makes this discovery so amazing. The discovery, which is highlighted in orange in the JWST's false color imaging, highlights the existence of prebiotic chemistry in the early cosmos and establishes the foundation for comprehending the conditions that could support life. Moving on, Maisie's galaxy, which was photographed by the JWST in 2022, was found to be among the first galaxies ever seen, existing only 390 million years after the Big Bang. Because it is located during a time when the first stars and galaxies were forming, this weak orange blob casts doubt on earlier theories about how galaxies emerge. A cosmic giant located in a galaxy that formed only 570 million years after the Big Bang, the JWST has also revealed the most distant active supermassive black hole. At 9 million sun masses, this black hole is surprisingly light in comparison to other supermassive black holes, which typically weigh more than 1 billion solar masses. Current theories of black hole origin and expansion are called into question by this discovery. But that's not all. The JWST imaging has revealed AZTECC71, a galaxy from 900 million years after the Big Bang, embedded deep within a cosmic dust cloud. Its obscurity points to a hidden galaxy population that was missed by earlier scans. By demonstrating the interaction between young stars, interstellar dust, and changing galactic architecture, this discovery offers a window into the dynamic early phases of the universe. Additionally, JWST detected 3 luminous objects that could be dark stars. Dark matter annihilation powers these fictitious beings. If verified, these stars could provide hints about the mysterious nature of dark matter and reshape our knowledge of the early energy sources of the universe. Dark stars, whose luminosities equal that of entire galaxies, offer an intriguing window into what was happening just after the Big Bang. Complex features like spiral arms and bars, similar to those present in the Milky Way, have been discovered in some of the earliest galaxies. These galaxies indicate that advanced galactic construction appeared much sooner than previously believed, having developed just 3.7 billion years after the Big Bang. All things considered, the James Webb Space Telescope functions as a time machine that gives us an unmatched ability to see into the early universe. Its findings fill in knowledge gaps and pique interest in the myriad cosmic secrets that remain unsolved. One observation at a time, the JWST keeps revealing the history of our universe, from the first molecules to the first galaxies. Let's return to the multiverse theory now. The multiverse theory and JWST, as previously mentioned, JWST has challenged pre-existing theories of galaxy formation by revealing galaxies that were formed only a few hundred million years after the Big Bang. Unexpectedly large and well-organized for their age, these galaxies raise the possibility that conditions in the early cosmos were impacted by as-yet unidentified causes, possibly indicating interactions or phenomena associated with a multiverse framework. By recording light that has traveled billions of years, for instance, the telescope can look into the past and find evidence of quantum fluctuations from the Big Bang. These differences are consistent with inflationary cosmology's predictions of a multiverse. In line with this model, the early universe's rapid expansion might have produced pocket universes, each surviving inside a bigger multiverse. The discovery of intricate organic structures and chemicals in primitive galaxies more than 12 billion light-years away provides another fascinating hint. These results provide a window into possible universes where comparable building blocks can exist under different circumstances, suggesting that the fundamental principles driving chemistry and life may not be as exclusive to our universe as previously thought. Furthermore, indirect evidence of bulk properties of spacetime that are consistent with multiverse predictions is provided by JWST studies of gravitational lensing, which occurs when light from far-off galaxies is bent by enormous foreground objects. According to string theory, which holds that our reality is only a brane in a higher-dimensional multiverse, such distortions may indicate higher-dimensional interactions. Furthermore, the finding of potential dark stars also sparks discussion about the multiverse. These mysterious formations cast doubt on our knowledge of dark matter and stellar evolution, and they make us wonder if other universes might be home to phenomena that are much outside the realm of our current physics. In a cosmos that is less than 4 billion years old, the telescope studies of galaxies that resemble the Milky Way suggest that order and complexity may develop far earlier or in a different way than previously thought. This supports the idea that the fine-tuned constants in our world could be just one arrangement of innumerable possible configurations in a multiverse. These discoveries challenge long-held beliefs about the universe's formation, composition, and development, opening the door for more research into one of cosmology's most important questions: are we alone? What is the opinion of Dr. Tyson? Well, a good deal, really. Neil deGrasse Tyson's perspective on the JWST and the multiverse. Scientists are now beginning to link the multiverse theory to findings from the James Webb Space Telescope. This also applies to Neil deGrasse Tyson. He has frequently explained that human brains aren't inherently able to handle the mind-bending complexities of cosmology because they were evolved for survival. We are not predisposed to think about concepts like brain worlds or quantum fluctuations. Rather, we are hardwired to fear predators like lions. However, that does not preclude us from expanding our knowledge. Tyson likens concepts that seem incomprehensible to the act of seeing water freeze. The concept of a liquid solidifying in a matter of minutes may seem as unfathomable to someone who has never seen it before as the multiverse seems to us now. Similar to this, JWST's discoveries, such as the identification of galaxies that were formed inexplicably and proof of dark stars fueled by dark matter, may seem strange at the moment, but they may eventually serve as the basis for supporting speculations about other universes. The once magical method of freezing water became ordinary with the invention of ice machines. For the past 100 years, quantum physics has been changing our knowledge of the universe. More than just redefining physics, the development of quantum mechanics opened a window into the most basic workings of the cosmos and gave explanations for events that were previously believed to be incomprehensible. According to Neil deGrasse Tyson, it is comparable to phase transitions, such water turning into ice, which is a well-known process that reflects the abrupt changes that take place at both the cosmic and quantum scales. Tyson points out that the quick expansion of spacetime during the early stages of the universe, a notion derived from the theory of inflation, is one example of such a phase transition. Understanding the motion of planets, stars, and even the way space itself bends around enormous objects like black holes is made easier by Albert Einstein's theory of general relativity. To put it another way, general relativity describes how large-scale phenomena behave, like as how gravity functions in our solar system and how humans are able to travel to space. It continues to be the most effective explanation for these enormous, cosmic occurrences. However, Tyson contends that at the smallest sizes, such as the level of atoms or subatomic particles, general relativity is ineffective. Herein lies the role of quantum mechanics. It addresses the strange, erratic behavior of minuscule particles such as photons and electrons. The principles that govern planets and stars are considerably different at this minuscule scale. This is a major issue in contemporary science. How do these two significant theories relate to one another? How can we develop a single theory that can account for everything, from the biggest galaxies to the tiniest particles? The solution lies in quantum physics. It enables us to explain the behavior of little objects. It explains, for instance, how atoms are assembled, why light behaves like a particle and a wave at different moments, and why particles like electrons can be in two places at once. Despite their bizarre appearance, these concepts are essential to comprehending the universe at a very small scale. Despite its attention to detail, quantum mechanics is crucial to comprehending the functioning of the entire universe, particularly when considering the origins of the cosmos. Tyson challenges us to consider what the cosmos might have looked like in the early stages, right after the Big Bang. The standard laws of physics didn't apply back then because the universe was so small, possibly smaller than a single atom. Quantum mechanics would have taken control instead. He shows that the universe's expansion and evolution may have been significantly influenced by the peculiar laws of quantum physics. For instance, quantum mechanics may have contributed to the universe's explosive expansion. In the post-Big Bang era, sometimes referred to as cosmic inflation, researchers continue to investigate the relationship between quantum mechanics and the overall evolution of the universe. We can attempt to comprehend how the quantum world influenced the development of everything we see now by examining the cosmos in its earliest moments, when it was so tiny that quantum effects were present everywhere. But when researchers used the principles of quantum physics to study the early cosmos, the results point to the potential for a multiverse. Indeed, many scientists believe that the multiverse is a real possibility since the mathematics underlying quantum mechanics really predicts that alternate dimensions might exist. Although the concept of a multiverse may seem like science fiction, Tyson argues that we shouldn't discount such theories just because we lack the necessary technology to support them. After all, a lot of scientific discoveries began as unproven theories. The notion that the Earth revolves around the Sun is one example of a theory that was formerly believed to be impossible. We may eventually be able to test theories like the multiverse to determine their veracity as science and technology advance. Our perspective on the world has already been altered by quantum physics. It has helped us comprehend the cosmos on the smallest scales, from particles to atoms, and has opened our eyes to new possibilities. Tyson also discussed his findings at a 2022 PBS Nova address titled "The Universe, Where Are We?", in which he discussed the JWST's role in studying cosmic inflation and its consequences for the multiverse theory. He underlined that the JWST might offer vital observational evidence in favor of theories about the early cosmos, such as cosmic inflation. Tyson claimed that knowledge of the formation and evolution of galaxies following this fast expansion may provide oblique proof of the existence of spatially isolated regions, which could result in the formation of completely distinct universes with unique physical laws. The multiverse theory is connected to this idea. Tyson added that the JWST might find quantum echoes that could indicate the formation of regions outside of our observable universe or patterns or cosmic anomalies that reflect the remains of cosmic inflation. The smallest remnants of actions that took place in the very early cosmos, including those that would have given rise to other universes in a multiverse scenario, could be revealed by these echoes being imprinted in the light that traverses great distances across time and space. In a number of interviews, such as his discussions on Star Talk Radio and his guest appearances on The Daily Show with Trevor Noah, Tyson has made it clear that, even though he does not believe the multiverse theory to be a proven fact, the development of tools like the JWST is creating new opportunities to test these radical theories. Although the multiverse is still theoretical and unproven, he pointed out that since we can now examine the universe in greater detail than ever before, we may eventually collect the evidence to confirm or disprove such theories. The JWST may be essential for researching the quantum fluctuations of the early universe because of its capacity to see the cosmos in previously unheard of detail, particularly at infrared wavelengths. In public speeches, Tyson has made reference to this. For example, during his discussion at the 2022 World Science Festival, he talked about how quantum fluctuations could leave measurable traces in the cosmic microwave background, which is a form of radiation that was left over after the Big Bang. Theoretically, the JWST could find these fingerprints, which would help researchers learn more about the mechanics of the early cosmos. Tyson frequently muses in his public presentations that scientific research is about pushing limits as much as it is about verifying existing facts. His perspective on the multiverse, especially as it relates to the JWST, stems from his conviction that advancing our observational capabilities is crucial to discovering more profound realities about the universe. As he has frequently said, the mysteries of the cosmos may appear far away and unsolvable now, but they may serve as the basis for upcoming scientific discoveries. These thoughts were also reflected in Tyson's interviews with other cosmologists at the 2022 American Association for the Advancement of Science Conference and on programs like CBS News Sunday Morning. Tyson talked about how instruments like the JWST could test some of the most speculative aspects of theoretical physics, such as the nature of spacetime, quantum mechanics, and the multiverse. Suppose, then, that the multiverse is established as an unquestionable reality. Then what? Evidence that the multiverse will revolutionize everything, the foundation of our understanding of the cosmos, our position within it, and the laws regulating everything would be drastically changed if the multiverse's existence were to be established. Numerous fields, including physics, philosophy, cosmology, and even how we see existence itself, would be affected. A thorough revision of present physical theories, especially general relativity and quantum mechanics, would be necessary to discover a multiverse. Both of these physics pillars function well on their own. While quantum mechanics deals with the subatomic universe, general relativity explains large-scale phenomena like planet motion. Complete opposites. But in many instances, the two are incompatible, especially when attempting to describe phenomena that exist on both scales, such black holes or the early universe. The current framework would probably be put to the test in a multiverse, which would require a single theory of quantum gravity to explain not only our reality but possibly an endless number of others. It would probably result in a paradigm shift or a new version of quantum field theory that includes the idea of parallel worlds or pocket universes. It would be necessary to revise the Big Bang theory, which holds that our universe began from a singularity some 13.8 billion years ago. The Big Bang might not have been the source of all reality if the multiverse is real. Rather, it might have been one of several localized Big Bangs that produced our universe. According to the multiverse idea, our universe might be but one bubble in an ever-growing foam of universes, each with its own set of conditions, constants, and physical laws. Our knowledge of cosmology would be stretched by this expansion, which would raise fresh queries regarding the possible beginnings of numerous universes and if they have any characteristics in common. Our conception of life itself would be altered if the multiverse were proven. Deep philosophical concerns would arise from the notion of numerous universes with distinct Earths, some with somewhat different natural laws, or perhaps the emergence of whole new life forms. Speculations about alternate realities, where various choices or events lead to drastically different consequences, could arise from the presence of parallel Earths. Our presumptions about biology, evolution, and the prerequisites for existence would be seriously called into question if it were discovered that some multiverse universes could harbor life forms that are radically different from our own. There would be revolutionary developments in space exploration as well. The first direct effect would be a re-examination of the definition of exploration. If any theoretical framework permits such an examination, space organizations may seek to understand or probe the boundaries of other universes rather than merely sending spacecraft to far-off planets or even stars. Understanding the physical characteristics of many worlds may lead to new approaches to exploring the unknown, even though investigating other universes may remain speculative for the time being. One could imagine missions to investigate quantum abnormalities, cosmic structures, or even the hypothetical boundaries between worlds. New technology would be needed to probe the multiverse. It would be necessary to create new kinds of space probes, ultra-sensitive detectors, and sophisticated quantum computing. For instance, by examining the development of galaxies, stars, and planets, the JWST is already transforming our knowledge of the far-off cosmos. However, future observatories may be built to search for signatures of other worlds if multiverse theory is confirmed to be true. If dark matter and dark energy, which are already mysterious, are connected to the existence of other universes, they may gain new relevance. Additionally, space organizations like NASA could increase the scope of their cosmic observations in order to find evidence of parallel universe effect. It might entail researching gravitational waves, cosmic inflation, or the cosmic microwave background. The first indication of a multiverse could come from any unanticipated irregularities in these measures. Furthermore, the identification of novel astrophysical object types or unexplainable events may inspire further investigation. Furthermore, the multiverse's discovery would raise fresh ethical and philosophical issues about interstellar travel. The idea of limitless universes may make people wonder if exploring is worthwhile and if finding new worlds would still be important if there were already infinite Earths or other Earths. Furthermore, examining the moral implications of multiversal knowledge may influence how people engage with their own reality and approach discovering new worlds, especially when it comes to protecting the planet and preserving life throughout the multiverse. The pursuit of a theory of everything that combines the strong and weak nuclear forces, gravity, and electromagnetism, all known forces of nature, would become even more urgent if the multiverse were true. Potential contenders for this theory, such as string theory and quantum loop gravity, would be evaluated not only for their capacity to describe our universe, but also for their ability to take into consideration the possibility of multiple universes. In order to explain the interactions between universes and the forces that shape them, the idea of brain cosmology, which postulates that our universe is a three-dimensional surface in a higher dimensional realm, would acquire new significance. All things considered, the discovery of the multiverse would revolutionize scientific thought. It would challenge our understanding of the cosmos and our place in it, making us rethink everything we believe to be true. Thank you for watching, and that's it for now. Was this video enjoyable to you? To ensure you don't miss our upcoming uploads, if you did, please think about liking, commenting, and clicking the subscribe button. Additionally, don't miss this very amazing video that is currently playing on your screen.